This is the last topic ever.
Thank you.
Ever. Last topic, last homework, last everything ever.
Thank God.
Standard reduction potentials. I want to talk to you about how this relates. Come on, Dave.
Come on, stop making out. Let's go.
How this relates to the voltaic cells we've been talking about. Okay, you missed it, Dayton. This is the last notes ever. So put that phone away before I take it for the day.
Wow, that's awesome.
Now look, here's what standard reduction potentials do. They measure in volts how likely it is that a reaction is going to be spontaneously reduced. Okay, and we can actually use this for several purposes, for two major purposes, really. So it's a tendency of the chemical to be reduced. And you know what reduction means. It absorbs electrons, and its oxidation state becomes more negative. All right, so the standard reduction potentials are compared to a standard hydrogen electrode. And there's a value associated with it, which I just gave to you on that sheet. Take a look at that sheet. Okay? I'm going to have a copy of it that's up here in a second. That sheet has numbers associated with each of those reactions. So it tells you how likely it is, the higher the number, how likely it is that this reaction wants to be spontaneous, it wants to happen. Now, what might I use this for? Well, you'll see. Okay, positive, first let me tell you what those numbers mean. Positive numbers mean the reaction is very spontaneous, and the higher the number, the more spontaneous it is, basically. Think of it that way. And negative numbers mean the reverse reaction, oxidation, is spontaneous. Okay.
Freshmen with questions beginning with the letters K and L. Please report to the conference room with your enrollment sheet. Thank you.
You're welcome.
All right. Now, those numbers are all located on, well, most of them are located on that sheet I gave you. However, in the homework tonight, there will be some that aren't on that sheet, okay? And they're in Appendix J, page A20, okay? So you can't find one of them on the sheet, which the sheet will be fine for us for the lab tomorrow. We're going to be doing for the for the test. But for your book, there are a few problems that aren't there. Okay. Now, what do we use these for? What's the point of this? Well, we just learned how to diagram a voltaic cell. Oh, I guess let me first just mention this real quickly. So these numbers up here, these larger positive numbers, mean that these reactions are highly spontaneous to be reductions. So chlorine really wants to be reduced. Guys down here, like lithium, he really wants to be oxidized. And that makes complete sense. Wouldn't I expect that? Okay, I think I would. All right, because lithium would rather do this reverse reaction where he's giving off an electron, because look where lithium is. If he loses an electron, he drops down to having an octet, okay? All right, whereas metals would want to gain, these guys up here would rather gain electrons, okay? And that makes sense, too. Look at there's fluorine, one of the highest numbers. You'd expect him to want to gain electrons. All right, now, here's the point of it. What's the point of having these numbers? Well, two major reasons. One, it helps us tell, given I put two cells together, remember what our voltaic cells look like. I have two half reactions, right? And I separate them. So in one I had copper and in one I had zinc, dear day, right? I told you what happened in that. I didn't have to. In the homework you're going to get tonight, it's not going to tell you whether the copper electrode got larger and therefore you knew it was copper +2 going to copper metal. And the zinc electrode got smaller and therefore it was zinc metal going to zinc +2. It'll just say, diagram the cell. And that's what I'm going to say on the test. How are you going to know who's undergoing oxidation in that reaction and who's undergoing reduction? These will tell you. And secondly, it'll even predict, and this is an amazing thing, I'm always amazed by this because electricity kind of blows my mind anyway. When we go back there in the lab tomorrow, you're going to actually have the last question on your lab is going to be find the percent error for the lab. You actually can predict, based on these same numbers, what the voltage of that cell should be when you hook it up to a voltmeter, how many volts you should get out of it. All right, so that's pretty cool. All right, those are the two things. Used to predict which element will be oxidized and which one will be reduced, and to determine the actual voltage of the cell, the potential difference, the electrochemical potential of the cell. Remember what voltage really corresponds to. The height of the waterfall, okay? The potential difference between, energy. I have amount of energy I have a possibility to make. Or not make, but be given off when that reaction occurs. As that water falls. Okay? Now, how exactly do you do this? And again, if the bell rings, I'm almost done with the notes. Or not bell, but if they call for you, just give me a minute. I'm sure they're not going to leave without you. So this is the last board of notes here. People who stay and everybody else should watch how to do the example problem. I'm going to do an example problem on here in a minute, too. You won't be here for that, I'm sure most of you, when you leave.
Where are you guys going?
College visit. Okay, so here's what you do. You simply look back at that same paper I gave you, and let's find the two guys that we used in diagram a cell right in your notes, right above it, the copper zinc cell. Okay, here's copper. Okay, he's on your sheet, same exact sheet you have there. Here's zinc right there. Okay, so let's just take a look at those two guys. Okay, there's copper, and there's zinc. Okay, all you have to do, first of all, is to determine who's going to be reduced. You look at who's the higher number. This guy's clearly higher than that guy, right? So that tells you that copper keeps this reaction stays the same, and this reaction goes backwards. And that's exactly what you wrote if you look back and see that. Secondly, the difference between those two, that is the actual voltage of the cell. A positive 0.34 and a negative 0.76 comes out to be a total of 1.10 volts. Okay? So what you do is because you're reversing that reaction, you make this a positive number, and you add the two together. A positive 0.76 and a positive 0.34 added together give you a 1.10 voltage. Okay? Or you can look at it two ways. You could do that, or you could just look at the difference between them. That's going to be the same answer. All right? So the more positive of the two guys that you're looking at is the one that stays the way he is. This chart is telling you how much. It's called the standard reduction potentials. It tells you how much they want to be reduced, how much they want to gain electrons. The higher the number, the more it wants to gain electrons. So given the choice between two elements, or two reactions, I should say, I'm going to pick the guy with the higher number as being the reduced guy. Now, by the way, again, you have to look at, if he's being reduced, I call him the oxidizing agent. That is his oxidizing ability, is how much he wants to be reduced. I know that sounds weird, but we went over this before when we talked about the redox reactions originally. We had a label, who was the oxidizing agent. Well, that was the guy who was being reduced. Who's the reducing agent? The guy who's being oxidized, right? Because he's responsible for either giving electrons or taking electrons. All right? To get the voltage, what do you do? To determine the potential or the voltage of the cell, you simply keep the guy who's being reduced the same, change the sign of the one being oxidized, and then add the two guys together. Okay? And I'm going to do an example of that in a minute. You are going to do an example of that in lab tomorrow. I already have it set up for you back there. I've got the copper strips out. I've got the zinc strips out. I've got the copper solution out and the zinc solution out. The really difficult part of a voltaic cell is usually the salt bridge. But because we have a neat way of taking care of that, I'll show you tomorrow.
That's going to be so much fun.
It will. And if we're really lucky, we'll light a light bulb.
Yay. Woohoo. So much fun.
All right?
Wait, grab that tomorrow morning.
Can't wait. All right. Okay, they copied? Okay. Here's your example. Copy that down while we still have time. I know they're going to call you any minute. I'm going pretty fast there.
Look at that.
No, are you guys literally all?
I don't know. Are they supposed to call for you guys? What is that? Those aren't even high school kids. They're like middle school, elementary school.
Don't take him too. Oh,
They're down there. We can't hear you. It's too late.
Just sit in the guidance office when they're in there.
Now you need to draw this. And by the way, on the test, I will, and on the lab too, I will have guys drawn for you to help save you some time. So while you're drawing that and writing that down, you'll see on the lab here, I've got it drawn for you. All you'll have to do is label both sides and predict the oxidation and reduction. And therefore also predicting the cathode, the anode, the positive, negative, and eventually the voltage of the cell. Wow, we're getting a lot in. I told you 940.
Miss Ferry told me 9:30.
good thing I'm not going. Otherwise, I'd be missing my awesome most favorite is class of the day, Chem 2.
Where are you going?
Are you going with them?
No. Everybody's there.
Yeah, those were middle school.
We have to go with Ron. Exactly.
All right, let's take a look up here. What's going to happen? All right, when you have a diagram of the cell, the first thing you're going to have to do is figure out who exactly is being oxidized and who's being reduced. So let's take a look at that. I've got the arrows. What's that? No, just you don't need, I kind of cut that off because it had other garbage on here. You don't draw those arrows. Just wait. All right, now look. Let's find the two guys that are happening on there. What are the two guys that are changing? Copper and sodium. All right, here's copper's. We already seen him. He's right here. Copper is 0.34. Do you find sodium on there? Find sodium on there.
Negative 2.71.
Wow. So we know who's going to keep their reaction the same. This one up here, he's higher. So I'll keep copper as this, and I'll reverse sodium. Let's do that.
Okay.
All right?
Sounds good.
So let's do it. It doesn't matter what side I do it from, but let's just put copper over here.
Okay.
Copper is he's being reduced. So it's Cu plus 2 electrons yields Cu. That's Cu plus 2 electrons yields Cu metal. He's being reduced. On the other side, sodium is being oxidized. So I've got, in order for him to be oxidized, he's got to give off electrons. I think we know what that's going to look like. It's going to be sodium metal becoming sodium ions plus 1 electron. That's how many it takes to do it. Sodium ions are plus 1. Now, I have to balance it like I always would for number of electrons lost and gained. So I put 1 in front of here. 2. I call this guy what he is. What is he? Oxidation. I call this guy what he is. Reduction.
Red.
Red.
Old red.
These don't change. You should all know which one's the anode and the cathode. Which is this. You have no idea right now. So you have 50-50 guess.
Cathode.
Easy way to remember that. What does that spell?
Red cat.
Red cat. There you go.
That's
right. Red cat. Like Schrodinger's red cat. And ox sat on a red cat. All right, the anox isn't going to work, but the red cat's okay, right?
Yeah, the red, that'll work.
I know.
Nobody will get that wrong now.
I know. However, this is the problem.
So
Charges.
they're
Yeah.
opposite of what they are.
They are. They're exactly right. They're the opposite of what they are for the electrolytic cell. But what were they for the electrolytic cell? And that's the problem. Do you remember?
Cathode's positive, anode negative.
Is the cathode positive and the anode negative?
Yes.
You sure?
Yes.
Yeah.
You have no idea. You're completely
Look at- he's
guessing.
looking himself
I'm looking
up.
myself. I don't even remember. How could you guys? Actually, the cathode is positive.
I was positive.
And the anode is negative.
See,
Now, look.
positive 'cause it was
By the
positive.
way, the reason this is, and I explained this last time, although it's kind of weird, this is your battery. This thing up here is not a battery. That's just a voltmeter. That's this thing right here, which we're going to use tomorrow. We're going to hook this meter up, positive and negative, and we're going to see that needle move when we hook it up to the battery you guys make. Okay? So this guy's generating the electrons. Who's generating them? Let's see. The guy who's giving off electrons will be this one. So those electrons are traveling up this wire, which basically is like your battery. They're traveling out to the electrolytic cells, let's just say. Now here's the crazy part about this. The reason the charges are opposite. This is negative here and positive there. This guy gave electrons off because he was in oxidation. What are those electrons used to do in the electrolytic cell? Reduce somebody, right? So the side that those electrons are going to go to is going to be the reduction, which makes him the red cathode, and therefore the cathode in the electrolytic cell is negatively charged. The battery part, the cathode, is positively charged. Yeah.
So, like the red cat, like cathode with reduction is always, it's like...
Yeah, these two never change. Oxidation and anode are the same here as they are there, but the problem is this oxidation, the charge basically is different because these electrons are being used. What's really flipping is not really, if you think about it, it's not really the charge. It's the fact that the oxidation reaction from the battery makes a reduction reaction in the electrolytic cell. They both have the same charge, but that's the reason they flip. Now, I know that's annoying. Believe me, I know it's annoying. I don't like, one of the things I don't like about electrochemistry is that you have to think about it every single time. Oh, by the way, you should also label, I'll have a better one here than this. This is a really kind of crappy one. You should also label, inside here are what kind of ions? Copper ions. Inside here are sodium ions. This electrode is copper, and this electrode is sodium. Okay, so you should label those. Now, there's still one more thing we have to do. Now, this was a little bit different than the previous cell we did for copper and zinc because this guy did not tell me who was oxidizing, who was reducing by giving me observations. This guy simply asked me who will be oxidizing, which one is which. You have no idea. You're not told by observations. Like copper got bigger, zinc got smaller. They weren't told that. There's something else about this we have to do, though, and that is predict what this voltmeter right here is going to read. I can predict that, and so can you. What was the number? I can't go back to that. But what was the number for copper? 0.34, correct?
Yeah.
And negative 2.
Yeah. So, but the sodium reversed itself.
So it's 2.7.
So 2.71, and then you simply add those two guys up. What do you get?
3.05. I did that in my head. I don't know if it's right.
Yeah, that's right.
There you have it. So that is what your voltage should read. Your voltage should be 3.05 volts. When you hook this up tomorrow, we're not going to use sodium. We're going to use copper and zinc. When you hook this up tomorrow, you'll be surprised how close you get to that. All right, now you can actually read it two different ways. I'm going to show you the voltmeter, basically, two different kinds that Schrader has. I'm going to try to get them over here, too. We'll see.
Freshman with last names beginning with the letter M, please report to the
All right,
conference room.
that guy's done. You've done everything that you would be asked to do, okay? And well, I should say one more thing about those electrons. Remember I was trying to explain, when I said the electrons go up here, they're going to come back down here. And what are those electrons used to do? They're used to reduce copper ions to copper metal. All right, to complete the circuit, it's not electrons that flow through the salt. This is a salt bridge. All right, they're not electrons that flow through there, but rather the ions are basically repelled or attracted, depending on how you look at it, and complete the circuit through the salt bridge, and therefore those sodium go back and do it all over again. Okay?
Awesome.
All right, now here's your homework right there, page 895, numbers 46, 48, 52, and 53. And that's what you'll be doing the rest of